Right, we are so close to finishing off the project. Let's see if we can't finish it off in this lesson today. So, last where we left off, we finally put all the labels and the squares. Couple things we could fix up. One is like this number over here does not look pretty, right? It's just got all of these decimal points, and it's taking up all the space. So how could we perhaps fix that? So, really simply, there's a function called round, which lets us round a particular number to a certain number of decimal places. I've actually did it here with A and B to say we're going to round those two. So what you can see with round is that you put in the number, so it takes two arguments, right? Round, like if I say 4.54, and then how many decimal places I want to round it to. Right, so this is already 4.54, but if I made this 4.548, this will round to 4.55 and take off the 8, right? So what we're now looking for is we have C, we're just wanting to round that. So we can just simply say round the square root of C squared, and we can say 2. And with that done, and we get an error somewhere, missing argument after list, maybe it just hasn't saved yet. But as we can see now, we're getting a much nicer, the numbers rounding over to 2 decimal places, which looks much nicer. So that's just one simple thing. The next one is we want to actually just visualize the area of the square with length side 205, what we were doing previously. So in order to do that, I wonder why this, there we go, now it's gone. In order to do that, we simply need to get a square with that side. So let's maybe put it somewhere like over here. Let's put it at like 100, 400. So we can say rect 100, 400. Now the reason, right, ideally we would put it on top of this. We'd put it on the actual hypotenuse. But you have to do quite complex stuff with rotations, which is beyond the scope of this video in order to get it here. If you want to take the challenge and be like, cool, how can I get this rectangle to sit at this angle? Give it a shot. Maybe we'll do a video in future on how to do that. But for now, I'm just going to put it somewhere so that it's sitting kind of in line with these ones. So I'm putting 100, 400, and C and C. Now when that saves, we can see we get this rectangle, which is then visualizing the area of the square with length side C, right? So the area of the red plus the area of the green is equal to this. So if you rearrange them nicely, you would get that. So that's what it's showing. The reason why this is useful is because I'm actually wanting to show you guys now, right? Like, let's come back. I'm going to pull up the distance formula over here again, right? This fancy looking formula over here, right? This is what we've done in reality, right? When we've gone through all of this stuff to find the length of A and B, and then we said C squared is equal to that, and then round, we've done this, but just in many more steps. So some people find this more simple, some people find this more simple. So let's go through it and show you why this, right, is the exact same thing as that, and then we can visualize it by showing 2 squares and making sure that they are the exact same. So let's go ahead and do that. I will open up this over here, and let's have a look. So we know when we have our triangle, it looks something like this. And we label this point 1, we label this point 2, point 3, and we're looking for the distance from point 1 to point 2. Right? So then we have A, B, and C, and we know that C squared is equal to A squared plus B squared. Okay, and in code now, we said, right, we said that A is simply P1x minus P3x, right? So coming back to this, we said that all that A is the distance between here to here. Okay, so that is P1x and that is P3x. But now we know that P3x is simply the same, it's the same as P2x. Right? We're not changing our x as we move from point 2 to point 3. So this is just P2x, right? It's the same. P2x is equal to P3x. We know that. We could, like, we've done it in code. let's see, P3x, P2x, okay? So we can just replace that over there. Now, similarly, to find B, we simply needed to find the vertical height. So we found this, okay? And now what we said there was we're saying, okay, P3y or P2y minus P3y minus P2y. And now similarly, P3y is the exact same as P1y, right? That's equal to P1y. Again, we could show that in code with what we did here. P3y is equal to P1y. So what we have, right, is then we can say from this that A is equal to P2x minus P1x, which is the same, or P3x minus P1x, which is the same as P2x minus P1x. So we can say x2, right, this one, P2x, I'm just going to get rid of the P, and say x2 minus x1. And B is simply y2 minus y1, right? It's this one minus this, right? So y2 minus y1, okay? So that's the distance for A, and then that's the distance for B. Now let's put that into this formula. If we have c squared is equal to a squared, and we know that A is equal to x2 minus x1. So we have x2 minus x1 squared. And B, we know it's y2 minus y1 plus y2 minus y1 squared. And then if we want to solve for C, we simply say C, the square root of both sides, and we get x2 minus x1 squared plus y2 minus y1 squared. Now that is the formula that you're seeing here. It's literally that, right? Instead of C, we have D. But we've just proven this formula just very simply and intuitively. And now this is a formula you can use to find the distance between any two arbitrary points anywhere in space. That's how you can find the distance between London and Paris, or Paris and Berlin, or Singapore and New York. So it's incredibly powerful. Now let's go ahead and test this, right? Let's just put this into code and see if we get the same thing. If we go ahead and, oh, I deleted a bracket over there. If we go ahead and just say let D now, right? So I'm going to use D, and I'm going to follow that formula. So the square root, right? And I'm going to say x2 minus x1. So that's point P1x minus, or P2x. We'll be able to see. Let's start for now. P2x minus P1x, all of that squared, plus P2y minus P1y, all of that squared. That is D. Okay, and now we could console.log it. Okay, we could see, cool, do we get the same C as D here? Console.log D. And when I open up my console now, we can see we're getting 223. And as I move this, it updates perfectly, right? So our D is exactly equal to a C. So it's the same thing, but we're just proving that. We could do this more visually, which might help. If I wanted to get because I want to be able to visualize that the area of the square with length side C or length side D is exactly the same. So what I could do here is I could put another rectangle, and now I want this rectangle to sit next to this other rectangle. I want a rectangle to sit over here, and I want to see that both of them are exactly the same. So I want to put it in the same position. So I'm going to take 100, 400, and I'm going to move it over by C, right? Because I want it to start where this rectangle ends. So I'm going to say 100 plus C, because that's going to be where the X position starts. And Y is going to say the same, 400. And now I'm going to, instead of doing D, I'm going to put D, or C, I'm going to put D and D. Let's change this color. Let's make this blue. Okay, perfect. Now we can see how this area, how it seems like the area of the blue square and the area of the white square are always remaining exactly equal. Now this is useful because you can test some of your assumptions around this formula. You can play with this formula and see what happens. Because oftentimes what people make a mistake is they'll put a minus between this, right? So put a minus instead of a plus. And now, all of a sudden, we actually, we get an error. Type error 2. Why, what is that? mean, that's weird. Right? And there we go, okay? And now we can clearly see this area is not the same, right? The area of the white square is simply not the same as the area of the blue square. So we know that this formula doesn't stand, okay? Let's test some other stuff that people sometimes make a mistake with. Does it make a difference if I switch the order in which I subtract it? If I do p2x minus p1x or like this, if I say p1x minus p2x, does it make a difference? And the answer is no, right? They're both staying exactly the same. So it doesn't matter the order. Let's test it with y as well. p1y minus p2y. Doesn't make a difference. And again, the answer is no, it doesn't make a difference. It doesn't matter what side, if we subtract p1x first or p2x first, because they're being squared at the end of the day. So when you take something squared, because it's just doing a similar operation to what an absolute value would do, right? Negative 5 times negative 5 is 25. The same as 5 times 5. So it doesn't matter the order in which you get it. Similarly, some people make the mistake of doing this. They would say p1x minus p2y, and then p1y minus p2x, maybe, right? So you mix up which one is which. And now again, very quickly, oh, weird. Okay, cool. So for certain values, it looks equal, but then you can see very quickly, sometimes you're just not going to get the same value. You're not getting the same area of the square. So you know that this formula isn't true as well. All right, that is the end of the Pythag project. We've now learned about distance formula, midpoint, and Pythagoras, and we're ready to do some more cool stuff with it. Thank you for joining me for this one, and I'll see you for the next Strive project.